Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 8 of algebraic topology. Our today's topic of discussion is the functor pi1. So as we have discussed earlier in our last lecture, that fundamental group is going to define another functor for us, which is going to be useful to study topological spaces. In this lecture we will see what is this functor pi1 and how it is related to the fundamental group, and towards the end of this lecture we will be studying some results which are helpful to calculate the fundamental group. So we know the category of pointed spaces. So the category of pointed spaces has objects which are topological spaces with a point which is you can just say is mentioned with this topological space. Okay, so these are the objects of this category. And what are the morphisms? So if I have two pointed topological spaces, then a morphism between them is going to be a function which is a continuous function from x to y, such that f of x naught goes to y naught. So these are the morphisms in this category of top star. Now we are going to define this pi1, which is going to be a functor from the category of pointed topological spaces to the category of groups. We will show that it's a covariant functor, and moreover if we have two maps h and k which are continuous functions and which are homotopic relative to this subset x naught, then pi1 of h is equal to pi1 of k. In other words, if we have two homotopic continuous functions or homotopic morphisms between two pointed topological spaces, then their image under this pi1 is equal. There is this little notation that we use. So if we have a continuous function from x naught to y naught, of course h of x naught is equal to y naught, then pi1 of h is going to be function from the group related to this topological space and the group related to this topological space. So from this group to this group, so we sometimes denote this map pi1 of h by h lower star. So let's see how we define this functor pi1, and we show its properties, that it's a covariant functor, and for two homotopic maps between two pointed topological spaces, their images are equal under this functor pi1. So let's first define pi1. So pi1, if I take image of any pointed topological space. Now with our choice of notations, most of you can guess that what's this image going to be. Exactly, this is going to be pi1 of x naught. So the fundamental group of loops which are based at x naught. Okay, so that's how we define image of objects of this category of pointed topological spaces. Now let's see how we define images of morphisms. Okay, so let h from x naught to y naught be a morphism between these two pointed topological spaces. How to define pi1 of h? And with our previous notation, this is the same as h lower star. So this is going to be a map between pi1 of x naught to pi1 of y naught. So how we define this map? So what are the elements of pi1 of x naught? These are the path classes of loops based at x naught, and if I take this image h lower star at f, then this is going to give me basically h composition f, so the path class of h composition f. So why this is well defined? Okay, so let's first concentrate on h composition f. So why this is a loop which is based at y0. Okay, so now h is a continuous function from x to y, and h of x0 is y0, and f is a loop at basically based at x0 and inside the space x. So f is basically a continuous function from I to x, and h is a continuous function from x to y. So we can take the composition and we can say that f and h composition. So first we apply f and then we apply h. So this is going to be a function from I to y. Okay, so this is a path in y. So is it a loop? Let's see, is it a loop or not? So first apply this function at 0. So what is h of f of 0? So f of 0 is x0. So we know that h of x0 must be equal to y0. Similarly, let's see what is h of f of 1. So basically, what is f of 1? So f of 1 must be equal to x0 because it's a loop. So this is equal to y0. So h is continuous function, f is continuous function, their composition is continuous function, and it's a function from I to y with initial and final point are same. So it's a loop with which is based at y0. Okay. Now let's see if this operation, if this image is well defined or not. So when we say image is well defined or not, it means that if I have f0 which is equal to f1, so the path class of f1 and f0 and f1 are equal, which means that f0 and f1 are homotopic. So this homotopy is a relative homotopy with respect to I dot. So if this happens, then their images are also equal. Of course, if they are the same elements, then if I want my H lower star map to be well defined, then the same elements should have the same images. Otherwise, the map is not going to be well defined. Okay, so what is H lower star of f0? So this is H composition f0. So we want to show that. Okay, so this is what we want to show, that the path class of H composition f0 is equal to path class of H composition f1. In other words, we have to show that, or we have to show that H composition f0 is homotopic to H composition f1. Okay, so if f0 and f1 are homotopic, then we can say that there exists a homotopy, let's say this capital F, such that f of x0 is equal to f0 and f of x1 is equal to f1 with some other condition imposed by this relative homotopy. So for example, when x is 0, for each and every value of t, this is equal to f0 of 0, which is equal to f1 of 0, and when x is equal to 1, then for each and every value of t, this is the same as f0 of 1 is equal to f1 of 1. And since these are loops, so these two f0 of 0 and f0 of 1 are equal. Okay, so we have this function f(x)t. So we are going to use this function capital F to define the homotopy between these two functions, H composition f0 and H composition f1. So let's see how we define this homotopy. So consider this function, which is f composition f of xt. Okay, so this is a function. So f0 is a path, f1 is a path. So this function is basically so f of xt is basically a function from I cross I to x, and now we are also imposing that at the end we are also taking image under H, and H is a function from x x0 to y y0. So this is going to be a function from I cross I, because I'll be taking images inputs from I cross I, but the output is going to be in y now. Okay, so let's see what is H of f of x0. So this is equal to So what is f of x0? This is equal to f naught. So basically this is equal to h composition f naught. Similarly, let's see what is h of f of x1. So this is equal to h of f of 1, because f of x1 is f1, so this is equal to h composition f1. Also, f is continuous, h is continuous, so their composition is continuous. So we have a continuous function from I cross I to y, such that at t is equal to 0 we have this map, at t is equal to 1 we have this map, and other conditions can also be seen. So for example, let's see what is h of f of 0 t. So when x is 0, and for each and every value of t, this is going to give me f naught of 0, so which is equal to f1 of 0. So basically f naught of 0, so basically this is going to be equal to h composition f naught of 0. And similarly we can show that when x is 1, then for each and every value of t, this is equal to f naught of 1 is equal to h composition f naught of 1, and of course which are equal to other values which can be calculated from here. So we can say that h composition f naught is homotopic to h composition. So we can say that this map, which is pi 1 of h, or which is also equal to h lower star, is well defined. Okay. Now we will show that this pi 1 of h, which is a map from pi 1 of x naught to pi 1 of y naught, is a homomorphism. So how to show that this is a homomorphism? So consider two path classes. Let's say we have P and another path class Q. So apply h lower star on this, and we will get h lower star P star Q. Okay, so this is equal to h composition P star Q. Now we have to show that, so to show is h lower star of P composition Q. Okay, so this is equal to h lower star of P star h lower star of Q. So which is basically equal to h composition P star h composition Q. Okay, so we can say that which is equal to h composition P star h composition Q. So we have to show that these two are equal. So this side 1 is equal to the side 2. In other words, we have to show that, or to show that h composition P star Q is homotopic to h composition P star h composition Q. Now let's see what is this function. Okay, so basically we are applying h on P star Q. So what is P star Q? So P star Q is equal to P of 2t, where t lies between 0 and 1 by 2, and Q of 2t minus 1, where t lies between 1 by 2 and 1. So what about h of P star Q? So this is basically equal to h of P of 2t, where t lies between 1 by 2 and 0, h of q of 2t minus 1, where t lies between 1/2 and 1. So basically we can say that this is exactly equal to h composition p star h composition q. So these two functions are equal, and so of course equal functions are homotopic, so we can say that this holds. So this 3 holds. So if this 3 holds, then we can say that this h lower star is a homomorphism of these two groups. Now we have to show that if h and k are homotopic, and this homotopy is relative to x naught, then pi 1 of h is equal to pi 1 of k. So if h and k are homotopic, then there exists a homotopy, let's call it f of xt, from x cross I to y. And of course there are some conditions imposed by this relative with respect to x naught, such that f of x0 is h and f of x1 is k, and the conditions imposed by this x naught. Now we have to show that pi 1 of h is equal to pi 1 of k. In other words, we have to show that this h lower star from pi 1 of x naught to pi 1 of y naught, and k lower star from pi 1 of x naught to pi 1 of y naught. So we have to show that these two are the same maps. In other words, we have to show that h lower star of f is equal to k lower star of f, where f is any arbitrary element of this fundamental group pi 1 of x naught. So what is this map? So this map is basically h composition f, and we have to show that this is equal to k composition f. Now we can consider this function f of xt of f of x. Okay, so it's a function. So we can say that we can see that h and k are functions from x to y, and f is a function. Basically it's a loop, so it's a function from I to x. Now basically we are starting from x, so basically this f of x, so we replace this x with f of x. Okay, so this is composed in place of x. So we can say that it's a function from I cross I to y. Okay, now if I take x t is equal to 0, then I will get h. So in other words, I will get h composition f. And if I take t is equal to 1, then I will get f of x 1, which is basically k, so k of f. So in other words, this is a function for t is equal to 0 will give me this function, and for k is equal to 1 it will give me this function. And this is continuous because f is a path which is continuous function, and this capital F is homotopy, so it is continuous. So we have a continuous function from I cross I to y, and which basically serves as a homotopy for these two functions. Of course there are some other conditions imposed by the relative homotopy, so I'm leaving this as an exercise to check the other condition. So we can say that pi 1 of h is equal to pi 1 of k. So in other words, if two functions are homotopic between two pointed topological spaces, then their related homomorphisms are same. Now let's recall what's a category and what's a quotient category. So we know what's a category: it has objects, it has morphisms, and it has the composition rule. And if I have an equivalence relation on the collection of all morphisms in a category, so these A and B belong to the category C, so objects of the category in fact, so the objects of the category C, such that the following conditions are satisfied. If f is equivalent to f prime, then f and f prime belongs to the same set of morphisms, and if f is equivalent to f prime, g is equivalent to g prime, then their composition respects this equivalence relation. Now if we define another category whose objects are the same as the objects of C, but the morphisms are basically the equivalence classes of morphisms, and composition is defined in this way, then this category is called the quotient category of C. Now we have seen that we have an equivalence relation on the morphisms of pointed topological spaces. So we can take that equivalence relation to be homotopy relative to x naught. So by taking that equivalence relation, and we can see that it satisfies all the conditions. So for example, this important condition, and so we can say that we have the category of pointed homotopy category. Okay, so what is a pointed homotopy category? So it's the category H top whose objects are the same as the objects of these pointed topological spaces, but what are the morphisms? So the morphisms in this H top star between two pointed topological spaces is basically the homotopy class of functions between these two pointed spaces, and we define the composition in this way. So roughly speaking, what we are saying is after this theorem which we just proved, if two maps are homotopic, then they have the same images. So instead of taking pi 1 from the category of topological pointed topological spaces to groups, we just take pi 1 to H top star, the pointed homotopy category, to the category of groups, because effectively it's a functor from H top star to groups, because if two maps are homotopic, then their images are same, so I don't need to consider these extra maps which are homotopic. So just take the morphisms to be these classes of homotopic maps. So in our next discussion, we are going to have a rough overview of another way to look at the fundamental group of X at point X naught. So let Y be a space. Each loop F from I to Y may be viewed as a pointed map from S1 1 to Y Y naught. So this S1 is basically a circle, and this 1, okay, so it's a circle, and this 1 is basically 1 0. So it's written as 1 because this circle is a group, and this element serves as the identity, so that's why we write it down as 1. Okay, so every loop in Y is basically can be considered as a pointed map from S1 1 to Y Y naught. Okay, so if this is the space Y, and we have a loop from 0 1, and this loop is F, and this is our loop, okay, and the initial point is Y naught, then this loop can also be considered as a pointed map. So the pointed map is F prime. So what does this map do? So it takes this point 1 0 and takes it to Y naught, and it takes the whole circle here. So in other words, a loop in a space Y is the same as a map from a pointed map from circle with this point mentioned 1 0, and this point goes to Y naught. Okay, so in other words, we can say that we have a bijection. So remember, in pi 1 of Y Y naught, we consider the path classes of loops, not just loops but path classes of loops. So every loop, every path class of loop is the same as this thing. So what is this set? So basically this is set of all morphisms in the category, in this homotopy category of pointed spaces, and and in this set every element represents a class of homotopy. Okay, so that's why we can say that every pointed map is the same as a path class of this fundamental group. And of course in this morphism, in this set of so in this family of morphisms up to homotopy, we can define multiplication. So we can operate f star and g star in the following way. So f prime is coming from some f, because there is a bijection between these two. If f prime is here, then there must exist f here, and g prime is here, then there must exist g in this pi 1 of y naught. So we just multiply f and g and take their prime. So in other words, when I multiply any two elements in this group, then it's another element of this group, and since there is bijection between these two sets, so I take the corresponding element in this set. So that's how we can define operation of multiplication in this set, which is basically the class or the family of homotopy class of pointed maps between circle and y naught. So pi 1 y naught is isomorphic to the home set. Okay, so since we are defining the multiplication in this class of homotopy class of pointed maps, so this is going to be an isomorphism, but we don't need to show it here. So roughly speaking, this is the important deduction. So roughly speaking, the fundamental group of Y is this set of homotopic morphisms from S1 to Y. Of course this is roughly speaking, because actually this is pointed maps and pointed morphisms, but we can say that fundamental group of Y at a point y naught is the same as the family of homotopy classes of morphisms or pointed maps between S11 and y naught. Okay, so fundamental group is basically a home set. Okay, and we can also define multiplication on that home set. So in general, we can define functors pi n. We use morphisms from Sn to the space. Our next result is that if we have a circle, then the fundamental group of this circle is basically isomorphic to Z. Okay, so the proof of this result will be done in our next lecture, but we are going to use this result to calculate some fundamental groups. So consider this proposition that we are going to prove in our further discussion. So pi 1 of x cross y is isomorphic to pi 1 of x cross pi 1 of y if x and y are path connected. So let's use these two results to calculate the fundamental group of the torus. So what is a torus? So torus can be considered as S1 cross S1. Okay, so we can take S1 circle, and we can take the same circle all the way along another circle, and if I keep repeating these circles, so basically I am taking cross of a circle with a circle. In other words, I'm placing this circle at each and every point of this circle, the base circle. Okay, so this is the base circle, and the space which we will get when we multiply this thing is going to be a torus. Okay, so so it will look something like this. Okay, so we can say that a torus is S1 cross S1. So if I want to calculate the fundamental group, so by this proposition, this must be equal to pi 1 of S1 cross pi 1 of S1. And from this theorem, pi 1 of S1 is Z, so we can say that the fundamental group of the torus is Z cross Z. So if you remember from our first lecture that this Z cross Z is basically a free abelian group. So what are the elements of this pi 1 of t? So let's for example consider this element 2 3. Okay, so this z is so one of the z is saying that, so if I take 2 from this, then whatever loop we are considering, of course in fundamental group we are considering loops. So what is this loop 2 3? So this 2 represents that we are taking twice, so we are taking a loop which is taking 2 rounds around this side of the torus and 3 rounds around this side of the torus. Okay, so this is 1 2 3 and then coming back to the same point, because this is a loop, so the starting and ending point should be the same. So that's a typical element of the torus, of the fundamental group of this torus. And now similarly we can consider other elements, let's say 4 10. So it means that it will take 4 rounds around this side, 3 4, and it will take 10 rounds around the other side, so 1 2 3 4 5 6 7 8 9 10. So it will come back to the same thing. So that's how the elements of this fundamental group look like. Now to prove our proposition, we are going to need the following definition. So if we have sets H and K, and if we have this map P and defined in this way, then this is a projection onto its first coordinate. So basically we are just saying that if I have R1 cross R1, then P of this is going to go to R1, and if I take elements XY from R1 cross R1, then it will give me the first coordinate. Okay, but of course this is R1, and in this case this is H, so H could have any type of elements. For example, this H could have ordered pairs or ordered triples or n tuples, but at the end we are just going to get elements of this H and ignoring these elements of K. Similarly, we can define another projection onto the second component. Okay, so this Q of XY is going to be equal to Y. So if we have a set L such that we have maps alpha and beta from H to K, then we can define another map alpha beta from L to H cross K. But the important thing about these alpha betas is, if all the functions are homomorphisms, then alpha beta is a homomorphism, and if all the sets are topological spaces and functions are continuous, then alpha beta is continuous. Okay, so this is the important point about this discussion. Now we have another lemma. If we have two functions phi naught and phi 1 which are homotopic, and this is free homotopy, so this is important, and these are continuous functions from x to y, and if we have a point x naught, okay, so let's say this is the point space x and this is space y. Okay, so we have a point x naught here, and corresponding to this point, of course, we can calculate the fundamental group. So we can calculate this object, so pi 1 of x x naught. Okay, now consider this path lambda. So what is this path lambda? So we have seen that this phi naught and phi 1, these are homotopic. So in other words, so these are functions from x to y, and if I have x naught, then phi of x naught is going to be one image, and similarly phi of phi 1 of x naught is going to be another image. Okay, because these are free homotopies and there is no condition on this x naught, and if they are homotopic, then in between them there'll be some other functions. So in this case, so phi of f of x0 is phi naught, and f of x1 is phi 1, and there'll be some other functions which are in between them for any t. So for example, this is phi t of x naught. So if we join all those images, okay, so in between them, so starting from t is equal to 0 to t is equal to 1, so if I join these images of f of xt, and basically I'm just considering these values by taking x to be x0 and varying t from 0 to 1, then I will get a path inside this y, okay, and this lambda, we are saying this path is lambda, okay. So let this be the path defined by this, such that lambda of 0 is equal to phi naught of x naught and lambda of 1 is phi 1 of x naught. Then there exists a commutative diagram. So what is this diagram? So this diagram says that if I have of course if there is a continuous function, okay, so phi naught is a continuous function, okay, so by assumption, so this is a continuous function from x naught to y, and the image of x naught, phi naught of x naught, okay. So phi naught is a morphism between these two pointed spaces. So according to our previous results, they will exist phi naught lower star, okay. So there exists this map, and this is going to be homomorphism. Similarly, there exists phi 1, which is going to be a function from this pointed space x naught to y phi 1 of y, sorry, x naught, phi 1 of x naught. So this is x naught, okay. So if we have this continuous function between these two pointed topological spaces, then I must get phi 1 lower star, which is basically a homomorphism between these two groups. So the lemma says that we can construct this phi, and this phi is going to be an isomorphism, okay. So let's see how to construct this psi, okay. So now inside y, so starting from phi naught of x naught, I have a map, sorry, I have a point, and then ending at phi 1 of x naught. So these points are basically f of x naught and t, okay, and there is a path from this point to this point, and we are calling this path to be lambda, okay. So we also know that if we have a continuous function from x naught to y phi naught of x naught, then there is this phi naught of star, okay. So which take loops of this pi 1 of x naught to the loops of this, and similarly loops of this goes to the loops of this. So let f be a path class of loop in pi 1 of x naught, okay. So we also know that the image of this is going to be a loop under this phi naught star and also under this, so I will get a loop, okay, over here and over here. Also these functions, okay, so these functions xt, so this is the function from x cross I to y, and for any particular value of t, so for example if I take t to be 0.5, then this is going to be a function from x to y, and the image of this path class or this loop which is based at x naught is going to be another loop at this point. So for example this is so this point is, so over here t is equal to 0.5, so basically this loop is, okay, so f of x 0.5 of f, so it's this continuous image of this loop in x. So basically this f is a loop at x naught in x. So these are all the continuous images of loops. Now consider this function h of x t such that this is defined as this lambda of x, where x lies between 0 and t, and this is equal to lambda of t for x lying between t and 1. Okay, so in other words, when t is equal to 0, then this is just the point lambda of 0. So we have seen that there is this path lambda. Okay, so this path is defined in this way that when we have 0, then this will give me, so the initial point is phi naught of x naught, and when lambda of 1, so lambda of 1 is phi 1 of x naught. So starting from this point to this point, so we are talking about this path. So when t is equal to 0, so let's see what is h of x 0. So when t is equal to 0, this is just equal to just 1 point, because between 0 and 1 this is just h of 0, lambda of 0, which is basically phi naught of x naught. Okay, so phi naught of x naught. And when t is equal to 1, so between 0 and 1 this is the whole path lambda. So we can say that this is the path, so this is 1 point is basically capital H of x 0, and this lambda whole path is h of x 1, and this h is basically a homotopy. And similarly we can define another function h prime of xt. So what is this function? So this is the inverse of this thing, so basically it will give me h of 1 minus x between x0 and t. So for example, when we have x is equal to 0, it will give me the initial point. Okay, and when x is equal to when t is equal to 1, then this I will be getting this final point, and this is equal to lambda of t whenever x lies between 1 and t, and this is constant. So basically what we are doing is this h of xt is starting from this point, and gradually as the parameter t increases, it is giving me functions. Okay, so for t is equal to 0.5, this function, and for t is equal to, let's say 0.75, I'll be getting this function. Okay, and it is constant beyond this thing. So as the t increases gradually, I'm getting I'm increasing in this direction, and this h prime does the opposite way. As I'm increasing, I'm increasing in this way. Okay, and now consider this homotopy. Okay, consider this homotopy h x t star. Okay, so what was the homotopy between phi naught and phi 1? It is f. So f of x t of f star h prime of x t. Okay, of course when we are composing it with f, then I'm replacing this x with f, and this is t. Okay, so we are taking star, and we are taking star on the variable x, and t is basically the parameter. Okay, so in the definition of star we have to replace one variable, so in this case this is this variable x and not t. So basically it gives me homotopy of loops at phi naught of x naught. So basically what we are doing, so when t is equal to 0, let's see what we are doing. So when t is equal to 0, what is h prime of xt? So for t is equal to 0, I'm just at this point, and when t is equal to 0, what is h of xt? So for t is equal to 0, I'm just at this point. Okay, and what is this composition? So basically it's giving me a loop. So when t is equal to 0, what is f of x 0? It's phi naught, so it's phi naught of f. So it's basically giving me this loop, and this loop is basically, so let's say this function is k of xt. So this is basically k of x 0. So as the t increases, so for 0.5, so when t is equal to 0.5, so over here now we have reached the point, and so it will be somewhere over there. Okay, so and in this way, so we have reached another. Okay, so in h prime of xt, so what we have done, so when t is equal to 0.5, then we are coming from the other way and we have reached this part, and we are also composing it, so basically we are getting a loop. Okay, so in other words, we can say that it is basically this loop at phi of x naught, so starting from this, going in this direction and coming back, so it's a loop at phi naught of x naught. So in short, this k of xt gives me homotopy of loops based at phi naught. Now we can see that this phi naught lower star of f is equal to beta lambda of phi 1 lower star of f. So I'm going to leave the details of this to you. Okay, so this is an exercise to see why this holds. So as a consequence of this result, we have the following proposition. It says that if x and y are homotopy equivalents, and then the induced homomorphism pi 1 of phi from this fundamental group pi 1 of x x naught and pi 1 of y phi of x naught is an isomorphism. So if we have this map x and if we have this map y, and x naught is a point, and there exists this pi 1 of x x naught, the fundamental group of path classes at x naught, and let's say this is phi of x naught, and if we have a homotopy equivalence between these two spaces, then the fundamental group pi 1 of x x naught is isomorphic to the fundamental group of y phi of x naught. Of course, as a particular case of this proposition, if we impose the condition that x and y are path connected, if x and y are path connected, then the fundamental group of y at any point is the same as fundamental group at every point. So similarly for the case of x, and so if x and y are path connected and we have a homotopy equivalence between them is a homotopy equivalence. Okay, so if this is the case, then pi 1 of x is isomorphic to pi 1 of y. Okay, so of course in particular you can say that if we have two topological spaces which are homeomorphic, then their fundamental groups are isomorphic. Of course, if they are homeomorphic, then they are also there also exists a homotopy equivalence between them. So the proof of this proposition is left as an exercise for you, and it is very simple, and it's also available in the book of Joseph Rotman. So our next proposition is where we are going to use our previous discussion of projections. So it says that if we have two topological spaces, then pi 1 of x cross y is isomorphic to pi 1 of x and pi 1 of y if x and y are path connected. Of course, we can only use this term pi 1 of x if x is path connected, because otherwise If it is not path connected, then we have to specify the point where we are taking this path classes of loops. But if X is path connected, then at each and every point the fundamental group is isomorphic to each other, so we can use the term pi1 of X. So let's see how to prove this thing. So let X naught Y naught is a point in X cross Y. Okay, of course the fundamental group at each and every point is isomorphic, but we have to choose a point if we want to calculate the fundamental group. So we have chosen this point X naught Y naught. So we have this pointed space, so we have this pointed space X cross Y, and the point is X naught Y naught. And similarly consider these pointed spaces X naught and Y naught. Now we have projections, so we have projections. Okay, so what are the projections? So P from X cross Y, X naught Y naught to X naught. Of course what we are doing is just ignoring the second coordinate. And similarly we have another projection Q from X cross Y, X naught Y naught to Y naught. So if we have this projection, then this implies we have a map P lower star from pi1 of X cross Y, X naught Y naught to pi1 of X naught. Okay, similarly we have another map Q lower star from pi1 of X cross Y, X naught Y naught to pi1 of Y naught. Okay, so basically we have the map from pi1 of X cross Y, X naught Y naught. So we have one map, let's say this is P lower star, and another map, let's say this is Q lower star, and this P lower star goes to pi1 of X naught, and this goes to pi1 of Y naught. And we also have projection, so we also have projection pi1 of X naught cross pi1 of Y naught. Okay, so just take the first coordinate to this, and the second coordinate, and just take the first coordinate to this. So this is basically some map. Okay, so according to our previous discussion, if we have this Q star and this P star, then there is this map P star Q star. Okay, and since this is a group, because this is a Cartesian product of two groups, or the cross product or direct product of two groups, and this is a group, this is a group, and this is also a group, being the fundamental group, and these maps P star Q lower star are homomorphisms of these two groups. So P lower star Q lower star, according to our discussion of projection, so this is going to be a homomorphism. Okay, so how to define this homomorphism? So we have homomorphism. Okay, so what is this homomorphism? So P lower star Q lower star. So what does this homomorphism do? So it takes this loop, and it takes it to P lower star F and Q lower star F. So how to calculate this P lower star F? So we know it from here, and how to calculate this Q lower star? We know it from here. Okay, and of course this is just equal to P composition F and Q composition F the class. Okay, so we have this map P lower star Q lower star. So what we needed to show is that this is isomorphic to this. In other words, we have to show that this P lower star Q lower star is an isomorphism. Now we can define a map theta from x naught, so pi 1 of x naught cross pi 1 of y naught to pi 1 of x cross y x naught y naught. Okay, so how do we define this theta? So theta applied on this path class G, path class H, so this ordered pair. So when you apply theta on this ordered pair, then this is just going to give me GH. Okay, so now it's a simple exercise to show that this P lower star Q lower star and this theta are basically inverses of each other. In other words, we have shown that this P lower star Q lower star is not only a homomorphism but also a bijection. So basically it's an isomorphism. So we have proved this result that we used to show the fundamental group of a torus is Z cross Z. Now we have our next important result. It says that if we have Sn, which is basically an n-sphere, so Sn is an n-sphere in Rn plus 1. So how do we define this thing? So it is the collection of all points x1, x2, xn plus 1 such that x1 square up to so on xn plus 1 square is equal to 1. So set of all points on this unit n sphere. So this proposition says that whenever n is greater than or equal to 2, then this is trivial. So we have seen that when n is equal to 1, then we have pi 1 of S1. So this is equal to Z, and we will prove it in our next lecture. But in this lecture we are going to show that whenever n is greater than or equal to 2, so above 1, every fundamental group of this n sphere is going to be 0. So how to show this result? It's relatively simple. So we have an n sphere. So when we take out this n sphere and we take just one point out, then this is homeomorphic to Rn. Okay, so it's basically an exercise for you, but we can observe this easily in the case of S2. So S2 is basically a sphere in R3. So if you take out the north pole, then each and every point on the sphere corresponds to a point in R2. And similarly, using the same strategy, we can show it for Sn minus x, where x is any point of the sphere. So let phi, so this f path class belongs to pi 1 of Sn. Okay, so based at some point, of course. So let's say that point is x naught. Okay, now we are going to show that this f is homotopic to a constant map, or it's null homotopic. So the strategy is very simple. So if we can show that, let's say if I have a so this f is a loop based at x naught, okay, inside this sphere. Okay, so let's say this is Sn. So if I can show that this path does not pass through this point x, which is the fixed point of the sphere, so if we can show that it doesn't pass through this point x, then this path, this loop f, is not just in inside Sn, but also is inside Sn minus x, because it doesn't pass through x. So strategy is to show that this f is basically belongs to Sn minus x. So if we can show that, and also we know that Sn minus x is homeomorphic to Rn, and we also know that Rn is convex. Okay, so if it is convex, then we have seen in an example that in a convex set every two loops are homotopic. So in other words, it has trivial fundamental group. So in other words, every loop is null homotopic. So if this path belongs to Sn minus x, so which implies that this path can be considered as a loop inside Rn, and so it will be null homotopic. Okay, so to show this, and since Rn has trivial fundamental group and it is also path connected, so we can say that has trivial fundamental group or is simply connected. So if it is simply connected, then we can say that this f, which can be considered as a loop in Rn, is homotopic to a constant map or is null homotopic. So that's the strategy. So we have to show that f belongs to Sn minus x. Okay, so consider this sphere, and let's say this is this path. So what we do is we consider an open ball B inside Sn. Okay, so let's say this is the open ball B. Okay, so in general this loop can have different paths. So for example, it can start from here and goes like this and this, and it can enter this ball many times, and then still end at this point x0. So what we are going to do is we are going to find, okay, so we are going to find another function g which is homotopy to this function f, and that function g does not pass through this point x. Okay, so let's say this is our sphere, and sorry, this is the open ball and the sphere, and we have this function which comes in and goes out, and of course and it is basically containing this point x. So this open ball B contains this point x, and this point x is different from the point x0 where we are taking this loop. So now consider f inverse of B. So B is open, so f inverse B is open. So since f is continuous, so continuous image of an open set is open. So what are the open sets? So f is a function from I to Sn, so the inverse image will be an open set in I, so where I is equal to 0 to 1 closed interval. So what are the open sets in 0 to 1? These are union of open intervals. Okay, so f inverse B is union of open intervals, so possibly infinite, so possibly infinite. Okay, now let's consider this point x, which is also point of this B. Now x, which is closed and bounded. Okay, a point in Sn is closed and it is also bounded. So by Hein-Borel theorem, this is a compact set. So since this Sn lives inside this Euclidean space. Okay, so this x is compact. Now what about the inverse image of compact? Okay, so in this particular case of Euclidean spaces, this f inverse of x is compact. Okay, so if it is compact and it lives, so the image, inverse image f inverse x will be contained in this union of open intervals. So f inverse x is contained in union of open intervals. So let's say these open intervals of ai, bi. Now the point is, since f inverse x is compact and it's contained in these union of open intervals, which could be infinite as well. But the compactness of this f inverse x says that these open intervals, so f inverse x is contained in finitely many union of open intervals. So f inverse x is contained in union of open intervals ai, bi. Now f inverse x is compact, so the compactness says that every open cover of f inverse x has a finite open subcover. Okay, so this f inverse x is contained in this union of open intervals, which could be possibly infinite as well. But then this f inverse x so must be contained in finitely many open intervals. So since f inverse x is compact, so is contained in finitely many, okay, so finitely many open intervals. So let's say these open intervals are so ai, bi, where I is equal to 1 to 3 up to n, where n is some finite number. So f inverse x is equal to union of these intervals ai, bi, where I is equal to 1 to n. Okay, now if we consider a particular open interval, consider this open interval, let's say without loss of generality, let's consider a1, b1. Now f of this closed interval a1, b1 is going to be a closed. So now f of ai, bi closed interval is going to be closed inside Sn. Why? Because f is continuous and a1, b1 is compact, and continuous image of a compact is compact, and this b is open, so this is contained in closure of b. Okay, so now this point f of a1 and point f of b1 are in the boundary of b. Okay, so since n is greater than or equal to 2, so the boundary of b is going to be Sn minus 1. So even if n is equal to 2, then we have S1. Okay, so even we have n is equal to 2, we have Sn minus 1, which is equal to S1, and which is a circle. And in circle, if we have 2 points on a circle, f of a1 and f of b1, then there exists a path connecting them. And of course, in higher dimensions, it is relatively simple to find a path from f of a1 to f of b1 in the boundary of b. So there exists a path, let's say g1 from, okay, so from f of a1 to f of b1. So we have a path from f of a1 to f of b1. So let's say this is a1, f of a1, and let's say this is f of b1. So there is a path between them. Okay, now the point is we have a continuous image f of this open interval a1, b1, and of course this is going to be a portion of this loop f inside this open ball b. And when we took the closure of this is going to be a closed set, and so f of a1, b1 belongs to the boundary of b. So there is a path connecting them. Okay, so this portion of the loop f, which is obtained by taking the image of a1, b1, which is basically a small interval of 0 to 1, is a loop inside b. And now we are going to see that loop. Okay, so basically there is going to be a loop. Okay, so now we are going to see that this loop from f of a1 to f of b1 is homotopic to this path g1. So why this happens? Because B is a closed set. It's basically a closed ball inside Sn, so which is convex. So once again, in a convex set, any two loops are homotopic. So basically f of a1 b1 is homotopic to g1. So this portion of the loop f, which is basically image of a1 b1, which is an open interval inside 0 1, so this portion of the loop f is homotopic to g1. And similarly we can see that other loops, okay, so these are homotopic to other g. So we can define g in general, so that this basically g2 is basically homotopic to f of a2 b2, g3 is homotopic to f of a3 b3, up to so on. So now we have defined a function which is homotopic to f, and it is contained in the boundary of b. So of course this function g, which is homotopic to f, does not pass through x, which is inside this ball b. Okay, so f is homotopic to g, and g belongs to Sn minus x. And since g belongs to Sn minus x, so g is null homotopic, and since f and g are homotopic, so f is null homotopic. So this is the end of the proof. Let's see what are the consequences of this result. So if we have any point x belongs to Rn, so the complement Rn minus x is homeomorphic to Sn minus 1 cross R. So in other words, if we want to calculate this pi 1 of Rn minus x, then this must be equal to pi 1 of S n minus 1 cross pi 1 of R. So basically using these results that pi 1 of Sn is trivial for n greater than or equal to 2, and pi 1 of S1 is z, which we will prove in the next lecture, and pi 1 of x cross y is isomorphic to pi 1 of x cross pi 1 of y, we have the following result. So if we have n is equal to 2, so in case n is equal to 2, then we have pi 1 of S1 cross pi 1 of R. Okay, so pi 1 of S is z, and pi 1 of R once again is trivial, so we have z. And similarly, when n is greater than 2, then we have pi 1 of S2 or higher, and these are trivial, and also pi 1 of R is trivial. So basically it's trivial whenever n is greater than 2. And similarly, we can use this calculation to show that R2 is not homeomorphic to Rn when n is not equal to 2. So how to show that R2 is not homeomorphic to R1? It's very simple, using the connectivity argument. So using the connectedness of R2 and R1, taking one point out from R1 will make it disconnected, and taking one point out from R2 will make it connected, so it still remains connected. So now using the previous argument, we can show that this R2 is not homeomorphic to Rn. So how to show that? Because we know that taking one point out from R2, okay, so what is the fundamental group? So we have seen that when n is equal to 2, this is equal to z, but we have also seen that pi 1 of Rn, when we take one point out, then the fundamental group is still trivial. Okay, so that shows that R2 is not homeomorphic to Rn. So proving Rm is not homeomorphic to Rn when m is not equal to n require the machinery of homology groups or higher homotopy groups, and we shall see this proof in our future lectures. So as I said earlier, in the next lecture we are going to see what is the fundamental group of a circle. This is the end of the lecture. Thank you very much, and Allah Hafiz.